Hello students, today we will start with a new topic Fourier series which is widely used in physics and engineering. It is used to describe the periodic nature of some physical phenomena. So straightforward, I am first writing the expression for Fourier series, then we will discuss about it. Fx is any real valued bounded and integrable function over an interval c to c plus 2 pi such that f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity an cos of nx plus bn sin of nx, where a naught is equal to 1 over pi integration over the interval c to c plus 2 pi f of x dx. A of n is equal to 1 over pi c to c plus 2 pi f of x cos of nx dx. B of n is equal to 1 over pi integral c to c plus 2 pi f of x sin of nx dx. So students, just look at this expression that fx is any real valued bounded and integrable function over an interval of length 2 pi. Then this expression, when we expand the function in form of trigonometric series, this is known as Fourier series, where a naught, an and bn, they are known as Fourier coefficient, and these expressions, these are known as Euler's formulas. So this is known as Fourier series of a function which is real valued and bounded over the interval c to c plus 2 pi, and to find this expression we will calculate these Fourier coefficients a naught, an and bn using these Euler's formulas. So before finding the Fourier series expansion of some functions, as we know, we have to use definite integral. So we will read about some properties of definite integral, that if we have to integrate any function of over the interval c plus 2 pi cos of mx cos of nx d of x is equal to 0, special case when m is not equal to n. Similarly, integration c to c plus 2 pi sin of mx sin of nx dx, this would also be equal to 0 when m is not equal to n. So we can use these type of results directly when we will find the Fourier coefficients a naught, an and bn. Now if we will discuss special cases when m is equal to n, that is integral c to c plus 2 pi cos of mx cos of mx dx, that is integral c to c plus 2 pi cos square mx dx, and that would always be equal to pi. Similarly, integral c to c plus 2 pi sine of mx dx, that would be equal to c to c plus 2 pi sine square mx dx, and that would be equal to pi. So these are the cases when m is equal to n. So when we will find the Fourier coefficients, if we find the function in this form sine and cosine, then during that we can directly use these results. Again, if there is the case that integral c to c plus 2 pi cos of mx sine of nx dx, that would again equal to 0 if m is not equal to n. So students, remember these results of definite integral that you will use frequently during finding of Fourier coefficients a0, an and bn. Also, we will use some more results that is integral minus a to a f of x dx, and you know it will be equal to twice integral 0 to a f of x dx when fx is an even function. What are even functions? Even function are those functions that if we replace x by minus x, that would again come equal to f of x. So if fx is an even function, then we will use this result. And second case, it will be equal to 0 if fx is an odd function. And what are odd functions? Odd functions, when we replace x by minus of x, then it comes out as negative of fx. Such functions are known as odd functions. So we will frequently use this property of definite integral. Also, during finding the limits, we will use some trigonometric results, that is sine of n pi. And students, you know sine of n pi is always equal to 0 for all n, where n is an integer. And then cos of n pi, it would be equal to minus 1 raised to the power n. Then odd multiple of pi by 2, it would also equal to 0. Cos of 2n plus 1 pi by 2 is again equal to 0 for all n. And for sine pi by 2 is 1, sine 3 pi by 2 is minus 1, sine 5 pi by 2 is plus 1, sine 7 pi by 2 is minus 1, and so on. So we will also use these results very frequently. Also, sine of n pi plus alpha, and it is equal to minus 1 raised to the power n sine of alpha. Cos of n pi plus alpha, and it is always equal to minus 1 raised to the power n cos of alpha. So students, these results from trigonometry we will use frequently when we will find the definite integral during finding the Fourier coefficients. So let's start with some problems of Fourier series. So now find Fourier series expansion of function x plus x square over the interval minus pi to pi. Let's start with this problem. Here f of x is x plus x square and its Fourier series expansion would be a naught by 2 plus summation n is equal to 1 to infinity an cos of nx plus bn sine of nx, where Fourier series coefficients are a naught, and we know that Euler's formula for a naught, and it would be 1 over pi. Now the interval is minus pi to pi, so we will integrate from minus pi to pi f of x dx. A of n is equal to 1 over pi integral minus pi to pi f of x cos of nx dx. B of n is equal to 1 over pi minus pi to pi f of x sine of nx dx. So students, we already discussed that we have to find the Fourier series expansion of the function x plus x square over the interval minus pi to pi, and we know that Fourier series expansion is always of this form, where a naught, an and bn are known as Fourier coefficients, and to find the Fourier coefficients we have already discussed Euler formulas. So now calculate the Fourier series coefficient. First we would calculate a naught, and a naught is equal to 1 over pi integral minus pi to pi f of x, and f of x is our function x plus x square g of x, and we can write it as 1 by pi minus pi to pi x dx plus 1 by pi minus pi to pi x square d of x. Why I have wrote this function in this form? Basically, as the integral is from minus pi to pi, so we can use the property from definite integral, and we know this function is odd function, so its integration we can directly write, its integration would be 0, and x square is an even function, so we can use again the property. So this would be equal to 0 plus 2 by pi integral minus pi to pi x square dx. Sorry, it's would be from 0 to. So students, again look what I have used, that if we have integral from minus a to a f of x dx, it would be equal to twice integral 0 to a fx dx, where fx is even function, and its integration would be 0 if fx is an odd function. So you can easily check that this x is an odd function and x square is an even function, so its integration would be 0, and its integration we will use the property, we will multiply it with 2, and we will write the limits from 0 to pi. So now solve it. It would be 2 by pi integration of x square is x cube by 3 with the limits 0 to pi, and it would be 2 over pi. Upper limit is pi, so it will be pi cube over 3 minus lower limit is 0, so it will become 0, and ultimately we will find it would be 2 by 3 pi square. So we have found first Fourier series coefficient A naught, and A naught would be 2 by 3 pi square. So I am writing A naught is equal to 2 by 3 pi square. So now let's find An. Now An would be 1 by pi integral from minus pi to pi. Fx is x plus x square cos of nx dx. Again, to use this property, I am writing it in this form: minus pi to pi x into cos of nx dx plus 1 by pi minus pi to pi x square into cos of nx dx. Now student, we can check. We know x is an odd function, cos is an even function, so their multiplication would be an odd function. And here x square is an even function, cosine is an even function, even their multiplication would be even function. And if you don't know these results, you can check it by replacing x by minus x. If f of minus x come out equal to f of x, then it is an even function, and if it is equal to negative of fx, then we call it an odd function. So if you do not remember the result, then you can find out and you can check that any function is even or odd. So it would be, as this is an odd function, so its integration would be equal to 0. You can check it at your own by replacing x by minus of x, and you have to keep in mind that cos of minus x is equal to cos of x. So this is an odd function, its integration would be 0 using the property of definite integral. And here this is an even function, so we can use this property and it would become 2 by pi integral 0 to pi x square cos of nx dx. Now we can integrate by parts, so its integration would be 2 by pi first function as it is, integration of second function minus derivative of first, integration of second dx with the interval 0 to pi, and it would be equal to 2 by pi. Now when we will put the upper limit, it would be pi square sine n pi over n, and we know sine of n pi is equal to 0. So when we will put pi, sine of n pi, and this would become 0. Again, when will we put lower limit 0? When will we replace x by 0 and even sine of 0? that is equal to 0. So in both the situation we will get 0 minus 2 by n constant will come out. Now again integrating by parts, it would be a first function as it is, integration of second function minus integral derivative of first function integration of second over the interval 0 to pi, 0 to pi, and it would come out equal to minus 4 by n pi. When we will put pi, it would be pi cos of n pi over n minus 0, because lower limit is 0 and it would become 0. Here we will have negative negative positive, integration of cos of nx, and it would be sine of nx over n with the limits 0 to pi. And now students, again just check it out, that to find this Fourier coefficient an, it is 1 by pi integral minus pi to pi f of x cos nx dx, and we use this property where fx is even or odd function, it become odd function, so its integration is 0. It is an even function, so we multiplied it by 2 and take the limit from 0 to pi, and we integrated it by parts. And now I am just erasing from here. So now put the limits. Here comes negative negative positive, it will become 4 pi over n square pi, and pi would cancel out, so we will get 4 over n square cos of n pi, and here it is minus 4 over n square pi, and now we will put the limits. Sine of n pi, we already know it is 0, minus lower limit is 0 and sine 0 is again equal to 0, so the whole term will become 0. And also we know that cos of n pi is equal to minus 1 raised to the power n, so it will become 4 into minus 1 raised to the power n over n square, and it will become 0. So students, in this way we will find Fourier coefficient a of n, and what it is 4 into minus 1 raised to the power n over n square. Now calculate or find the Fourier coefficient Bn. Now what is Bn? Bn is equal to 1 over pi integral from minus pi to pi. Now our function is x plus x square sine of nx dx. Now it can be written as 1 over pi integral from minus pi to pi x into sine of nx dx plus 1 over pi integral from minus pi to pi x square sine of nx dx. Now students, you know that cos is an even function and sine is an odd function. So this is odd, sine is an odd, odd into odd, this will become an even function. Here this is an even function, sine is an odd function, so even into odd, it will become an odd function. So students, if you know the concept of even odd function and you know this property of definite integral, then you can use this property directly during finding the Fourier coefficient. So being it is an even function, we will use the property, its integration would become twice 2 over pi integral from 0 to pi x into sine of nx dx, and being x square sine nx as odd function, so its integration would become 0. Now find the integration of this function using by parts. First function, second function. So first function as it is, integration of second function with the limits 0 to pi minus integral from 0 to pi, derivative of first function is 1, integration of second function is minus cos nx over n dx, so it will become 2 by pi. Now we will put upper limit pi here, it will become negative pi cos n pi over n minus, it will become 0 because lower limit is 0. When we will replace x by 0, this whole term will become 0. Now negative negative will become positive, integration of cos nx is sine of nx over n with the limits 0 to pi. Now it will be equal to 2 over n cos n pi, and cos n pi is minus 1 raised to the power n, and here it will become 2 over n pi, and sorry, we can write it as n square pi. Now sine n pi minus sine 0, and we know both sine n pi and sine 0 both are equal to 0, so this whole term will become equal to 0, so we will left with 2 by n minus 1 raised to the power n. So we can write bn is equal to 2 by n minus 1 raised to the power n. So students, we know the Fourier series expansion of any function is of this form, where a naught, a n, b n are Fourier coefficients, and to find these Fourier coefficient we use these Euler formulas, and using the simple properties of definite integral we can calculate or we can find these Fourier coefficients. And we found that a naught is 2 by 3 pi square, a n is 4 by n square minus 1 raised to the power n, b n is 2 by n minus 1 raised to the power n. So now just replace in Fourier series expansion a naught, a n, b n by these results. So x plus x square is equal to a naught. A naught is 2 by 3 pi square, we will replace, so we will get pi square by 3 plus, now a n is 4 by n square minus 1 raised to the power n cos of nx plus bn is 2 by n minus 1 raised to the power n sine of nx. So it can be written as pi square by 3. Now I am writing for n is equal to 1, n is equal to 2, n is equal to 3. So when n is equal to 1, it will be 4 by 1 square with minus 1 raised to the power 1 cos x plus 2 by 1 minus 1 raised to the power 1 sine of x. For second, it will become, when n is equal to 2, it will be 4 by 2 square minus 1 raised to the power 2 cos of 2x plus 2 by 2 minus 1 raised to the power 2 sine of 2x. When we will replace n by 3, it will become 4 by 3 square minus 1 raised to the power 3 cos of 3x plus 2 by 3 minus 1 raised to the power 3 sine of 3x, and so on. So ultimately we can write it as pi square by 3 minus 4. I am taking negative as common, so it will become cos of x over 1 square cos of 2x over, it will become negative cos of 2x over 2 square plus cos of 3x over 3 square, and so on. And for the second term, it would be negative. We will take it out as common, 2 as common, so it will become sine of x over 1 sine of 2x over 2 sine of 3x over 3, and so on. So this is the Fourier series expansion of this function x plus x squared. So students, in this way we can find the Fourier series expansion of so many functions over the interval of length 2 pi. So just practice some more questions from your textbook, and in next part we will discuss about the Fourier series expansion of the function when there is an interval of length other than 2 pi. Thank you.